Okay, well let's move on to Anova, and Anova is the same as what we've been doing so far, but Anova is an hypothesis test where we're testing more than two samples. Um, so it follows the same logic that the previous hypothesis test did, except um, there's a more detailed steps involved in the process. We will still find a F obtain, which is equivalent to a Z obtain, and we'll determine whether or not um, it's in the rejection region. If it's in the rejection region, that means that we reject the null hypothesis, which means that there is a statistically significant difference. Uh, if it's not in the rejection region, we accept the null hypothesis, which means that there is no statistically significant difference, and any differences are due to random chance. However, the first thing that we need to do for an ANOVA is we have to set up our table. So let's use this example, right? And I'm going to read it out loud. Do older citizens lose interest in politics and current affairs? A brief quiz on the recent headline stories was administered to random samples of respondents from each of four age groups. Is there a significant difference? Following data represent members of current respondents. So what we see here is that we have a data set, and what we can see is that we have four samples or four cases, and we can list them. High school is one, young adults is two, middle age respondents is three, and retirees is four. So what that basically means in our notation is we use the lowercase k to signify that. And the lowercase k signifies that there are four categories, right? And so we give the number four. The next thing that we have to do in this process is that we need to determine the n, and the n is just the total number of observations. So what we see here is that we have four cases, and we can count it, but we have 12 observations in each category. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. These last ones are simply the sums of each one of the categories, right? So we know that there are 12 observations and there are four categories. That is simply 4 multiplied by 12, so that gives us an n of 48. Okay, so we have our k, which is our number of cases. We have our n, which is 48. And the second thing we need to do is we need to determine um, the mean for the entire deal here, the whole mean for the entire data set, right? And that's pretty simple, right? So we'll use this this x with the line over, which stands for x bar, to determine the mean for the entire data set here, and that's pretty easy too, right? So we've already got the sum of each column. So all we do is we add all of these up, right? And that would give us a number. If we added them all up, that would give us the number 259, right? And all we would do is divide that by the frequency, which is 48, right? And remember the formula. It's n divided by the frequency, right? And in this particular case, the mean is 5.396, and we will just round that up to 5.4, right? So we're going to continue to set up the tables in the next steps. But before we can get to the steps of ANOVA, we have to set up the table. Okay. So we moved on to our next step, and our next step is we're continuing to set our table up. What you can notice from the table is that we've added additional categories with these x squareds, right? So what we have to do for any table in Anova is we have to square our observations and then total them at the bottom, right? So a square is simply multiplying something by itself, right? So we'll see for this first observation is 0 times 0 gives us 0. 1 times 1 gives us 1, and so forth going down the line, right? So we do that for each of the categories, right? So we do that for 1, we do that for 2, we do it for 3, and we do it for 4, right? So we square each one. And we go down the line. 1 times 1 is 1, 1 times 1 is 1, 2 times 2 is 4, 2 times 2 is 4, 2 times 2 is 4. The square of 3 is 3 times 3, which is 9. 5 times 5 is 25, going down the line, right? And we did that for each of our categories, right? And then after we square them, we took the sum. So this is the sum of all of the squares for each categories, right? And this is key for the following steps, right? But we also have to do something else. We need to find the mean, that means the average, for each of the categories, right? So let's find the average for high school, which is 15 to 18. So that would be the total here, which is 44. And that total would be divided by 12 because there's 12 observations. And that would leave us with a mean for the category of, and we designate it with X bar with a subscript of a K. That would leave us with a categorical mean of 3.67, right? And we would do the same for each one, right? So this would be 53 divided by 12, and that would give us a categorical mean of 4.42, right? And we do the same here, 67 divided by 12, and that would give us a categorical mean of 5.58, right? And we do it for the last one, which would also be 95 divided by 12, which would give us a mean of 7.92. So these would be each one of these individual scores here are the means for each of the categories. And what we've done here is we've set up the table for now we can do the Anova steps, right? So if you're doing a homework problem or a quiz, you need to get your table to look like this, right? So you just write down what you have, right? So we already found the mean for the whole data set. It was actually 5.396, but we rounded up, and the mean is actually 5.4, right? Our n is 48. Our number of categories is 4. So we have all the information that we need, and we squared each one of our categories. So we have all the information that we need to actually conduct the Anova steps. Okay. So the first step in the process of Anova is step 1, and we'll call it step 1, is the sum of squares, and we designate that as SST. That's a T. Okay, so this is step 1, right? And the formula for that is sigma x squared minus n over the mean squared. We'll multiply by the mean squared. Now, this is step one, right? So we've actually done all that. So we know that this uppercase sigma just means to add things up, right? So we've already found the sum of all of our squares, right? After we square these observation, right? And we mark those totals here, right? And here, and here, and here. So for this first part of the formula, it is simply 220 plus 339 plus 441 plus 795. Right? And that's minus our n, which is 48, which we have it up there, times the mean squared, and our mean is 5.4 squared, right? So if we did all the math here, it would come out to be on this side, it would be 1795 minus 48 times the square of 5.4. So you have to do the math. So the first thing you would do is you would multiply 5.4 times 5.4, and you would then multiply what you got from that by 48. And if you did all of that, you should come out with 1399.68. And you just do the simple math, just subtract that, and your SST for step number one is 13. I'm sorry, I screwed that up. Erase that. So your SST for step number one is 395.32. Okay, so this is step one, and we just found our SST of 395.32. My advice is that you keep a scrap paper and you write down SST equals 395.32, because there are many steps, and you're going to come back to the numbers. Okay, so now we're moving on to step number 2, and let's designate it as step number 2. And step number 2 is the sum of the squares between, and we designate that as SSB, the sum of the squares between, right? It has the formula for SSB is the uppercase sigma of the sum of NK, and multiply that by each individual mean of each category minus the mean squared, right? So this is a step that most people make their errors, right? So this NK is simply the number of observations in each category. So for NK, we got 12 observations in each category. If we count it, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's it. So NK is simply 12, right? This X bar with the subscript of a K is the mean, which is here, for each one of our columns. So if we set this up, it is simply set up this way, right? So the sum of squares between is simply, for our example here, will be 12 over our first, this is our first one, our first mean of our first category for high schoolers, which is 3.67, minus the mean, which is 5.4, squared. Okay, and we'll do that for each one of the four categories. So the next one would be 12 over the second category, which has a category mean of 4.42, and that's 4.42. You got to excuse my bad handwriting there. So it's 4.42 minus 5.4 squared plus 12 over our next category mean, which is 5.58 minus the mean 5.4 squared over our last one, and hopefully I can fit it in there, which is 7.92 minus the mean of 5.4 squared, right? So the way you would do this is you would do everything in the parentheses first in the squares, right? So for the first one, you would simply subtract 3.67 from 5.4, and what you got from that, then you would then square it. That just means what you got in here, you would just, what we got in here, in this box here, you would then just square it or multiply it by itself. Once you do that, you should come out with 35.91, and we'll do the same for the next one. It should be 11.52, and for the next one it should be 2.76, and for the fourth one it should be 76.2, and you just add those up, and your SSB should equal 126.39. And remember, write these down on a note sheet, because you need these numbers as you continue. Okay, so we're moving on to step number 3, right? Oh, gotta fix that. So we're moving on to step number 3. And step number 3 is simply called the sum of the squares within, and it's signified as SSW. It's one of the simplest ones that we do, right? So it is simply SSW simply is what we just did before, right? It is the sum of the squares minus the sum of the squares between. So we figured those out in step number 1 and 2, right? So SST was 395.32, and SSB was 126.39. And if we do the simple math, we get our SSW of 2. Oh, I'm sorry, I messed that up. Let's fix that. We get our SSW of 268.93. Right? And we're going to move on to step number 4. The first 2 steps are generally the steps where folks make the most mistakes. The last steps are okay. So we're moving on to step number 4. Keep doing that. Moving on to step number 4, which is simply where we find the degrees of freedom, right? So in step number 4, there's degrees of freedom within, and there's degrees of freedom between. So we'll find both of these. These are pretty simple, right? So the degrees of freedom within is simply n minus k, and the degrees of freedom between is simply k minus 1, right? So, I mean, we don't have to do too much here to figure this out, right? Our n is 48, and our k was 4. So our degrees of freedom, let me fix that bad handwriting. So our degrees of freedom within is simply 44. And our degrees of freedom between is simply 4 minus 1, which gives us 3. So our degrees of freedom between is 3, right? And you want to write these down too, because it's going to take us to our critical area where we determine whether or not this is in the rejection region or not, okay? So our next step, which I'll call step 5, is basically where we're estimating the population variance. So let's call this step number 5. Okay. And step number 5 is also, it's pretty simple, but we got to use information that we've gotten so far, right? So in step number 5, we're going to find the mean of the square within and the mean of the square between, right? So they're pretty simple formulas, right? So let's say the mean of the square within, let's just call it MSW. And MSW is simply the square within, which we found in the previous step, is divided by the degrees of freedom within. And the mean of the square between is simply the sum of the square between, or SSB, divided by DFB, or the degrees of freedom between, which we've already found, right? So I'm going to switch colors so I don't confuse anybody. This is pretty straightforward too, right? So our SSB was 126.39, and our degrees, that's a 9, and our degrees of freedom within was 44, right? So that gives us an MSW of 6. Yeah, it gives us a MSW of 6.11, and our SSB was okay. So let's move on to step number 5, and in step number 5, we're estimating the population variance. And so let's just call this step number 5. Step number 5 is not that difficult, right? So in step number 5, we're finding 2 things. We're finding the mean of the square within. Let's just call it MSW. And the mean of the square between, right? And both of these are pretty simple, right? So the mean of the square within is simply what we found in our other steps is SSW divided by the degrees of freedom within. And the mean of the square between is simply SSB divided by the degrees of freedom between. So these are pretty simple, right? So let's just do um, MSW, or the mean of the square within, right? And SSW was, from our previous, that's why we write it down, was 268.93 divided by the degrees of freedom within, which was 44, right? So that'll give us an MSW of 6.11, right? And our mean of the square between is just SSB over the degrees of freedom between. And our SSB, or the sum of the squares between, which we found out earlier, is why we write it down, was 126.39 divided by our degrees of freedom between, which was 3, which gives us a MSB of 42.13, right? Okay. So this will move us to our F obtained, right? And our F obtained is the same as our Z obtained. It is what we're going to compare to our critical area, right? So we'll talk about that as step number 6. Okay, so this is step number 6. This is our F obtained. Okay, and let's think of the F obtained the same way that we did in our previous hypothesis test. This is the same as a Z obtained. We want to know if this is actually in the critical region. If it's in the critical region, then we will reject a null hypothesis, and there is a statistical significant difference. If it's not, there is no statistical significant difference, and all of this, any difference was just due to random chance, right? This is pretty simple, right? So the formula for F obtained is simply MSB, which we just got, divided by MSW. And what that, our MSB was 42.13 divided by 6.11. And that will give us a F obtained of 6.9, right? So we want to know if this 6.9 is in the rejection region or if it's outside the rejection region, right? If we were just given a p-value, and our p-value was 0.03, we would then determine that this was not in the rejection region, because remember, we want our p-value to be over our alpha, or our level of significance. And for political science, we always rely on a p-value of 0.05. So if this wasn't at 0.05, then we would say that we would accept the null, and there is no statistically significant difference. However, this would actually have a significant p-value, which we can use our books to determine. Okay, so we're going to do that now in our last step here. We'll call it step number 7, and you'll have. Okay, so let's call this the final step. This is step number 7, right? All right. So you should turn to your in your book to Appendix D. So it's Appendix D in your book, and it's on page 451. Right? And it's called the distribution of F. So there's a table, at the there at the top of the table, there's an N with the subscript of a 1. So it should look like this, N1, and it has an arrow pointing this way, and N2 has an arrow pointing this way. Okay, so if you have one of the old books, you'll see that there should be an arrow for N1 that says degrees or DFB, right? And for N2, there should be an arrow that says DFW, right? So what this signifies is the degrees of freedom between and the degrees of freedom within, which we already found, right? So we found that the degrees of freedom between was 3, right? So for that top row, for that N1, it has the arrow pointing toward the right. What you would do is go over to your degrees of freedom between, which was 3. So you go over 3, right? So once you go over 3, you come down to your degrees of freedom within, which is the N2 with the subscript, right? And our degrees of freedom within was 44. So we'll come down all the way till we get to 44. But what you'll find is that there is no 44. It stops at 40. Well, it goes from 40 to 60. So we would take the number that is closest to our 44, and without a doubt, 40 is closer to 44 than 60. So what we get is we get a critical score of, let's call it F critical, of 2.84. Okay, so that is our critical score. That is the this is the rejection region. Okay, is our 6.9, our F obtained, in the rejection region? It is certainly in the rejection region. It is in the rejection region because the rejection region starts at 2.84, and anything greater than 2.84 is in the rejection region. And 6.9 is certainly greater than 2.84. So what does this mean? Since 6.9 is in the rejection region, it means that we will reject the null hypothesis. There is a significant statistical difference between the age groups. The younger and older voters are different. There is a statistically significant difference. We have rejected the null hypothesis. And that concludes Anova. And there are examples in your book, and I would suggest that you go back to the book for examples, or you can work along with the video again. I think it'll help you out.